So the 2's complement system uses 2 complement numbers. So it's different than the 2's complement number or the 2's complement form, but it is actually a way of representing signed numbers on a computer, because we can't just put a plus or a minus beside them. This allows us to use the operation of subtraction by just using adders, right? Because when we subtract numbers, a computer only uses adders to add. So the computer needs to be able to perform subtraction with its adder. Therefore, it needs some sort of a system where we can add a sign bit to it to say whether it's positive or negative, because that's how our computer likes to do its work. So in this system, we represent positive numbers one way and we represent negative numbers another way. So first, let's look at these, how we represent positive numbers. So positive numbers are kind of easy. We can keep positive numbers in their true binary form, and then we append a 0 to its bit. But when we represent negative numbers in the 2's complement system, we have to take the 2's complement form and then append a 0. So let's take a look at what that looks like actually on a computer. So the computer will have a certain number of bits in its memory. And in order to represent a positive number, for example, positive 16, or a negative number, negative 16, to represent a positive number, we are going to append a 0 to a sign bit. And the sign bit is placed in front of the most significant bit. So if these are our bits, then this is my most significant bit is here, right? And what it means is you want to add another bit here. I'm always going to make it look different. And that bit is a 0. And the rest of the number is in its regular form. But for negative numbers, I'm going to append a 1. So the system is going to append a 1 here. And this 1 basically says, hi, this is a negative number. What you're about to read, all of these are a negative number. It's a negative number. What number is it? I haven't talked about that yet. And when your computer sees this starting with a 0, it says, hey, this number that's sitting over there, I'm just going to take away the example 16 here, so we don't have an actual example in there. So when I see a 0 in there, what that means is, hi, I have a positive number coming to you. Positive number coming to you. And that's the most critical part, is sort of that first number. And then we have to represent the rest of it a little bit different. And remember, I said the easy part is the positive numbers and the hard part is the negative numbers. So in the positive numbers, I just keep this the same. And negative numbers, I have to take the 2's complement. All right, so it's a little bit more time consuming. Let's do an example here. Represent positive 13 base 10. So that's like decimal number, which, you know, humans speak decimal numbers. So 13 base 10 in the 2's complement system. I said system. I did not ask for the 2's complement of 13. I said represented in the system. So the solution to this then would be, I would keep it in its regular form. binary form. And then I would append a sign bit of 0. So let's put it in its regular form. So in order to get 13, I would probably steal an 8, a 9, 10, 11, 12. I would not take the 2, and I would take a 1. 8, 9, 10, 11, 12, 13, base 2. There we go. I put it in its regular binary form, and then I want to append a sign bit to it. So in this case, I would go, okay, my 1 sitting in here, my 0 sitting in here, my 1 is sitting in here, and my 1 is sitting in here, and I want to append a sign bit, but I have to append a sign bit of 0 because this is a positive number. There we go. I assigned a sign bit of 0. Therefore, 0, 1, 1, 0, 1 is positive 13 base 10 in the 2's complement system. But wait, there's more. But wait, there's more. What if I told you that I wanted it to be, say, a 8-bit 2's complement system? I want it to be an 8-bit. Then I would actually have to say, okay, well, there's 1-bit, 2-bit, 3-bit, 4-bit, 5-bit, 6-bit, 7-bit, 8-bit, right? I need 1, 2, 3, 4, 5, 6, 7, 8. And I want to get rid of this one. I don't need this one. And then what you want to do is you just want to fill in with the leading sign bit, 0, 0, 0. So now 0, 0, 0, 0, 1, 1, 0, 1 is positive 13 base 10 in the 2's complement system. Oh, sorry, in the 8-bit 2's complement system. What would you have to do for a negative number? You would have to append a 1, and you would also have to put the number in the 2's complement form. So let's do that as an example. Negative 9 base 10 in the, let's do 5-bit 2's complement system. All right, so I want it to be a 5-bit system. I want it to be a negative number. So what I would do then is I would have to, solution, I would have to take the 1's complement. I need to take the 1's complement, which a 9 is an 8 plus a 1, right? Taking the 1's complement means that each of these digits gets inverted. And then I need to take the 2's complement, which means I add a 1 to it, right? And then 0 plus 1 is 1. 1 plus 0 is 1. 1 plus 0 is 1. 0 plus 0 is 0. And then I append a sign bit. And if it is a negative number, I literally have to append a 1 as the sign bit. So here's my sign bit, and I append a 1. So therefore, negative 9 base 10 in the 2's complement system is 1 0 1 1 1 if it is in the 5-bit 2's complement system. So the 2's complement system is a systematic way of representing signed numbers for your computer. And if it's a positive number, then the sign bit is a 0. If it's a negative number, the sign bit is a 1. If it's a positive number, you keep regular binary, or which is called true binary form. If it's a negative number, you have to take the time to put it into 2's complement form.